Hello. Today we're going to start our unit on graph theory, which is a branch of topology. We had talked a little bit about topology in previous videos, but we're going to get into some basics on graph theory, starting with this introductory video and then going from there and getting into some more specifics with some different types of graphs and so forth. All right, so graph theory. Well, if you're thinking of algebra and thinking of graphs with x, y coordinates, that is not the kind of graphs that we're dealing with here. This is something different. There's vertices and edges and things, but you don't have to. It's just the definitions and all that are going to be different. So start approaching this with a very open mind and just be willing to learn the basic definitions right now in this unit, and that'll go a long way to helping you understand what's going on. All right, so early origins of graph theory actually come from a little story, true story. There was an 18th century town called Königsberg in Prussia. And this town was built on both sides of a river called the Pregel River. Hopefully I'm pronouncing that correctly. So we have this river. And then the town is on both sides of it. And in order to get across this river, they had little bridges, little footbridges built. So they weren't huge. They weren't like Sunshine Skyway type bridges. They were just little footbridges. And some of the footbridges do still exist. Others you can find where they were located, but they're not there anymore. But they also took advantage of the fact that there was two little islands out in the middle of this river. And they connected mainland, the riverbank areas, and these islands all together with these little bridges. So I think I'll use orange. They had one bridge like this. They had one bridge like this. They had two more bridges this way. They had a bridge connecting the islands. And they had two more bridges this way. And the question was, often the people after dinner at night, they'd like to take little walks around their town. And they were playing this little game and tried to figure out, can we take a walk? And can we use each bridge exactly one time each on our walk? Or are we going to be stuck using, at least one of the bridges more than once? So it's kind of this question. Can you take a walk and use each bridge exactly once? They didn't have to necessarily get back to where they started. They just wanted to use each bridge exactly once. So they weren't even asking to get back home. They were just saying, can I just use each bridge once on my walk at all? And they puzzled over that for a long time until a man named Leonhard Euler took the problem into his own hands, and he thought about it. And in the process of thinking about it and solving it, he developed graph theory. And you can use graph theory concepts, techniques, etc., to help you to answer this question. And I am not going to answer this question for you right now. In fact, I encourage you, puzzle it out. See for yourself whether you can take a walk in Königsberg and use each bridge exactly once. And you might make some interesting observations. I'm not going to say yes or no yet. Tune into the next video to find that out. And in the next video, we'll discuss how we know the answer. The math behind it, but how did Euler figure out the answer? But that's just the introduction. That's the hook to tell you that where graph theory first started coming about. So Mr. Euler This was in the 1700s. 1707 to 1783 was his lifetime. And he helped develop this branch of topology. And in graph theory, we do draw graphs, but graphs are sets of points, vertices. And you can have you can have just one point, or you can have multiple points in a graph. And these points are connected by edges. Now, edges do not have to be straight, like when you think of polygons. They can be curvy. You can have more than one edge coming out of the same vertex. You can have more than one edge connecting two of the same vertices. You can have loops coming out of vertices. So that's what a graph is. It's sets of points connected with edges. And these edges are line segments or curves, or loops, whatever you need. A loop specifically is an edge that connects a vertex to itself, just like you would think. In casual conversation, if you know what a loop is, that's what it is in graph theory too. So you have the starting point, it could take you around back to the same starting point. But he used the concepts he basically drew a graph of the situation in Königsberg and started looking at it that way and seeing some of the patterns that came about with his vertices and edges and possible ways you could travel along those edges to each vertex to decide whether it was doable or not. All right, so here's an example of a graph that I pre-drew. It's a lot prettier than the one I was just sketching a minute ago. In this graph, you have vertices A, B, C, and D. So the vertices are marked by the little dots. Notice that just because two edges cross each other doesn't mean there's a vertex there. Like right here, there's no vertex. The edges do not touch. Don't think of those as intersecting. Don't think of it that way. So you can't go there and then take a turn. Think of it like an overpass. Think of it like a highway overpass. You're not going to jump off the overpass onto the other road to keep going. They do that in the movies, but in real life, that would have dire consequences if you tried to do that. So if you were going on an overpass over I-4 or something, you're not going to be able to suddenly do a sharp turn and be on I-4. The edges here, we usually will label edges with the two vertices that are at their endpoints. So like edge AB has endpoints A and B for vertices. You could call it edge BA if you'd rather. That part doesn't matter. Later when we get into talking about paths and things, the direction is a little more important. So then you would consider direction when you're deciding which letter to put first. But from A to B is an edge. From B to C, between B and C, that's an edge. Between B and D is an edge. Between A and D is an edge. Then the loop AA is considered an edge too. It starts at A and it comes back around and ends at A. That loop, that is an edge. There's an edge between A and C. There's an edge between C and D. So that all those together make up this graph that we have here. Now, some of the other definitions that we start to look at when we're analyzing these graphs include the degree of a vertex and then whether a vertex is even or odd. The degree of a vertex is the number of edges coming in or out of that vertex. So you start looking, just focus in on the vertex and see how many edges are sprouting from it. And count those up, and that's the degree. If you've got a loop, you consider that as 2. Because you've got two parts of the loop sprouting out of that vertex. If it's an even number, it's an even vertex. If your degree is odd, it's an odd vertex. So that's like this graph here. Vertex A, if you look at it, you have 1, 2, 3, 4, 5 sprouts coming out of it. Sprout is not an official graph theory term. I just feel like that's the best way to explain it. Definitely you will not see that in a graph theory book. But anyways, it's just kind of how to think about it, the little, what's coming out of that vertex. So yeah, vertex A has 5 of them. Vertex B, you start counting, you got 1, 2, 3. That's where that 3 comes from. Vertex C has 1, 2, 3. Vertex D has 1, 2, 3. And those are all odd numbers. The 5, 3, and 3. 5, 3, 3, 3. Those are all numbers. So this particular graph has all odd vertices. That's not always going to be the case. I mean, you could have all even vertices, or you could have a mix of odd and even. But this particular one I drew just turned out to have all odd vertices. Kind of an interesting relationship between the degree and the number of edges is that if you add up all the degrees in your graph, that's always going to be double the number of edges. Now, if you think about it, each edge has a vertex, 2 vertices. There's one on each end. Or in the case of a loop, we'll look at it. It's one edge with the with that one vertex there. But you're going to end up with, like with the loop, your degree is 2, even though it's sprouting out of that one vertex. So degree is always twice that. So like this one, you have 1, 2, 3, 4, 5, 6, 7 edges. And then earlier we figured out all the degrees were 5, 3, 3, and 3. And when you add that up, you get 14. So 7 times 2 equals 14. And that's going to be true for all of your graphs. It's kind of a cool little pattern there. All right, and as I kind of briefly mentioned a few minutes ago, these graphs, we don't have to just look at them as static pictures. We can start thinking about, like, what if we dropped an ant on there and had the ant move along the graph? Moving from vertex to vertex only along the edges. And they have to stay on that same edge until they get to a new vertex. You can't switch edges until you are at a vertex. So adjacent vertices are 2 vertices in a graph connected by an edge. So like when I talked about edge AB earlier, A and B are adjacent vertices because they're connected by edge AB. Path is a sequence of adjacent vertices and the edges connecting them. So when you're doing a path, you have to go from vertex to vertex along an edge. And you can't just suddenly switch directions until you can't switch edges until you get to another vertex. A circuit is a path that begins and ends at the same vertex. So like when I talked about the loop, AA, that's a circuit too, because if you take off from A and go around the loop and come back to A, you started and ended at the same vertex. So here's that graph once again, same one from earlier. And I denoted the path. There is a path from A to B, and then from B to D. When I'm doing this, I like to put little arrows to show my directions along the edges so that I can keep track of which way I've gone and which edges I've used. This will be important later in the future videos. I also did a circuit. Let me switch colors maybe. I went from A to B. Then I went from B to D. Then I went from D to C. And then went from C back to A. And that's a circuit. And that's how we would denote them. We would use the names of the vertices. We'd list the vertices in the order that we visit them. Put little commas in between as we're listing them. And then on the graph, we would draw the little arrows to show, which directions we were going. So that's just one example. And that graph, that's not the only paths and circuits possible. You have a lot of different paths and circuits possible. Like another path might be, you always have to even start and end in the same, you don't have to use the same starting point. Like I might have started with C and said, okay, from C, let me go to B. And then from B, I might have said, okay, let me go to A. And then from A, I might have said, let me do the loop. And then from there, I might have decided to go to D. And then from there, I might have decided to go back up to B. Nothing wrong with that. So that's an example of another path. And there's also other circuits you could take. There's multiple circuits. They don't all have to start and end with the same vertex. I mean, once you are doing a circuit, starts and ends with the same vertex. But I'm saying that I can have circuits that don't start and end with A. I could have one that started and ended with D if I wanted. I could go from D to A to B to C to D. Do that instead. So there's all kinds of options. A little bit more about these paths. In a connected graph, any two vertices in a graph have a path connecting them. It's not saying that every two vertices has an edge connecting it. It's saying there's a path. Like A and D here don't have an edge connecting them, but you can go from A to B to D, and there's a path. Or you could go, like from B, you could go to B to D to C. There's a path. From D, you can go D to B to A. There's some kind of a path connecting, or you could go D, C, A. So that's a connected graph. In a disconnected graph, there's at least one pair of vertices not having a path connecting them. Like, there is no way to get from A to D. There's also no way to get from A to C in this graph, or from B to C, or from B to D. So although you have some pieces that are connected, like A to B is connected, so C and D, but there's other pieces that are not connected. So that's a disconnected graph. And so far, don't the names just make sense? Like, most of the time in graph theory, when you listen to the names of things, it's like, oh, that's common sense. Okay. It really is. It's not, so I think that learning the definitions shouldn't be too much of a burden for this. All right. And earlier I talked about the bridges of Königsberg problem. But in graph theory, a bridge is technically, the definition of a bridge in graph theory is something a little different than something that crosses you over water or over land. In graph theory specifically, a bridge is an edge that when you remove it, it turns a connected graph into a disconnected one. So like in this particular graph, the edge from B to D is a bridge. Because as soon as I remove it, my graph went from connected here to disconnected. And I don't know, you can think about the real world also. Way back in 2004 with the hurricanes, when we had Charlie, Francis, Jean that went over Polk County. I happened to live in Poinciana and experienced all three of those. When Charlie came up on shore there down near Sanibel or Captiva area, down there near Fort Myers and all that, it wiped out the bridge that connected Sanibel to the mainland. And so for a long time, the residents in Sanibel and Captiva could not drive across to get to the mainland. So that bridge, when it was removed by the hurricane, it created something that went from connected to disconnected. And they had to start taking a ferry back and forth again. I mean, years ago, before the bridge was built, they had to do a ferry, but they had to go back to using boats and ferries to get back and forth until the bridge was repaired and stuff into a state that they could drive across it again. So if you think about like the real world, graph theory is the same idea. A bridge is an edge that if you wipe it out, suddenly pieces are disconnected. Okay, I had another example I wanted to show with bridges and so forth. Let's see. Let's draw a graph and let's revisit all of our definitions. Just kind of do a quick summary of all of the definitions we've covered so far. All right. Typically, you'll see vertices labeled with like capital letters, but they don't have to be. Those don't have to be the names. The names can be other things. Like if I was doing a graph based on the map of the United States, I might use the state abbreviations as my names on my vertices, and that's perfectly fine. But more often than not, you are going to see, capital letters. So I'm going to name these Q, R, S, T, U, V. Okay, so my vertices are Q, R, S, T, U, V. And then you can see the edges in there. You've got, edges between Q and S, edges between Q and R and S and U, T, U, T, V, U, V. So there's what? 1, 2, 3, 4, 5, 6, 7 edges. So 6 vertices. And then there's 7 edges. I'm not going to list them all right here, but there's 7 of them. And then for our vertices, let's see what the degrees are. Q, R, S, T, U, V. Let's see what the degree of each vertex is. All right, coming out of Q, I've got 1, 2 coming out of that, so degree is 2. So that makes that vertex even, because that's an even number. R also has 2 coming out of it, so another even one. S has 3 coming out of it, 3 edges coming out of it, so that degree is 3, so that's odd. T has 2 edges coming out of it, so that's even, degree 2, even. U has 3 coming, 3 coming out of it, so that's degree 3, odd. And then V has 2 edges coming out of it, so that's degree 2, even. The numbers of even and odd are going to be important in the future too, but for now we're just learning to identify whether it's even or odd and what the degree is and that kind of thing. So this graph, if we add up all the degrees, we should expect it to be 14 because there's 7 edges. We got 2 plus 2 plus 3 plus 2 plus 3 plus 2. That's 14, yep, which is twice the 7 edges. So that makes sense. That adds up correctly. Some examples of adjacent vertices include Q and R. They have an edge connecting them. S and U. So maybe you could say S and U are adjacent because they have an edge connecting them. But not adjacent would be Q and T. Because Q and T have a lot more in between them than just one edge. Possible paths, like one possible path in this might be from Q to S to U to T. One possible circuit might be something like T to U to V to T. You'll go all the way back to T if you start at T. So that's review there. Right now it is connected. This is definitely a connected graph. I can get from any one vertex to another with some kind of path. They don't have to be directly adjacent, but I can get from Q to T following some kind of path. But let's see, does this graph have a bridge? I see one bridge. Let me change colors here. Actually, let's highlight it. Right here. This is a bridge. If I were to remove that edge right there that I highlighted, suddenly this graph would go from being connected to disconnected. So this graph definitely has a bridge. If I took that out, if I took out edge SU, then my graph not only would be disconnected, but it would have 2 components. It would still be a graph, but it would have 2 separate parts that weren't connected. So there you go. I threw another word in there. I threw component in there. What is a component? Components are connected pieces of a graph that cannot be enlarged while remaining connected. To find a component, we start with any vertex of the graph and find all edges and vertices that are included in all possible paths from that vertex. So you can have this really complicated looking graph, and it may be disconnected. The components are the pieces that are connected, but you can have multiple components that are disconnected. All right, let me draw a graph and demonstrate. Okay, this graph's going to have vertices A, B, C, D, E, F, G. It's going to look like this. Looks kind of like a stick figure jumping for joy with some kind of random dot near it, maybe a star or something. Maybe like almost looks like a constellation, like a jumping for joy constellation. And maybe this little random dot's its dog next to it, jumping for joy too. I don't know. A random little star there. All right, so here's our constellation, our graph. So here's a graph. And this graph is disconnected. I can see that immediately with the vertex D. That is one of the components. So just draw vertex D. So that's out. So I took that out. All right. Then let's do one that starts with vertex A. All right, vertex A has an edge connecting it down to vertex F. Vertex F has edges out to vertex E and out to vertex G. But as far as that graph is concerned, that's it for that piece, that component. So that's a separate component on this graph. A, E, F, and G. And then let's do another color. Let's do blue. So if we start with C now, it has an edge connecting it to B, and that's it for that one. So that's another component. So this graph has 3 components. It's a disconnected graph, but then we just were able to identify those 3 components. If you wanted to create a connected graph, you would have to add in some bridges. You'd have to add in something that was able to connect all, like at least, probably 2, I'm trying to think if I could do 1 edge. Nope, you would need 2 edges at least to turn this into a connected graph. Because you would need something connecting D to one of the components, and then you would need something that connects the pink and blue components together. It all have to be somehow connected. Or maybe blue and pink both need to connect to D, vertex D. So you need at least 2 edges. You could add more. There's nothing wrong with adding more edges if you wanted to or needed to. But that's pretty much it. All right. Well, I hope you enjoyed this introduction to graph theory. When we tune back in, we're going to actually answer that burning question about the bridges of Königsberg. So please do think about it, play with it. Don't be too quick to try to find the answer. But maybe think about what you just learned with graph theory and think like Euler. Think about how you might apply that to the bridges of Königsberg problem and then try to make some generalizations and some conclusions. All right. So until then, have fun drawing graphs, and I'll see you soon.